High-temperature cuprate superconductors have long fascinated physicists, but the true secrets behind their remarkable properties have remained elusive until now. The story is more complex than most realize, and the latest breakthroughs are challenging long-held assumptions. But here's where it gets controversial. The material that has been studied the most isn't actually the one with the highest superconducting temperature. Why? Because it's simply easier to work with. However, recent advances have finally allowed scientists to grow crystals of the top-performing superconductor, opening the door to fresh insights that could reshape our understanding. For years, researchers have concentrated on a cuprate known as Bi-2223, a compound that superconducts at 110 Kelvin. -106, yet a closely related cuprate, Hg1223, actually boasts a higher critical temperature of 134 Kelvin. But its crystals have been notoriously difficult to produce in a form suitable for detailed study. Cuprates are a family of ceramic materials characterized by layers of copper and oxygen atoms arranged in planes known as QO2 planes. These planes are essential to their superconducting behavior. Both Bi-2223 and Hg1223 are tri-layer cuprates, meaning their crystal structure contains 3 such QO2 layers stacked within each unit cell. The key difference lies in their composition. Hg1223 contains mercury atoms within its structure, while Bi-2223 contains bismuth atoms instead. In a significant development in 2024, a Japanese research team, including many of the same scientists who have studied these materials before, succeeded in synthesizing a new variant called Hg-Re1223. This compound is structurally similar to Hg1223, but with some mercury atoms replaced by rhenium, which helps stabilize the crystal and makes it easier to analyze. Impressively, this new material exhibits a superconducting critical temperature of 130 K, close to that of pure Hg1223. The lead researcher, Masafumi Horio from the University of Tokyo, and his colleagues used a sophisticated technique called angle-resolved photoemission spectroscopy, ARPES, to probe the electronic properties of Hg-Re1223. ARPES is a powerful method that allows scientists to map out the energy levels of electrons in a material as a function of their momentum. This mapping reveals crucial details, such as the size of the superconducting energy gap, how electrons interact with each other, and the relationship between electron energies and their wave-like behavior within the crystal lattice. Here's how ARPES works. The material is illuminated with ultraviolet or X-ray photons of a specific wavelength, which causes electrons to be ejected from the surface via the photoelectric effect. By measuring the energy and emission angle of these electrons with a high-resolution spectrometer, researchers can deduce their original binding energies inside the material. This process requires accounting for the energy of the incoming photons and the material's work function, the minimum energy needed for an electron to escape the surface. Why is this important? Because the binding energy of electron pairs, known as Cooper pairs, directly relates to the superconducting gap. These pairs are responsible for carrying the supercurrent without resistance. The superconducting gap represents an energy range where no electron states exist, meaning that any excitation within the material must have at least this minimum energy. This gap effectively prevents low-energy disturbances like electron scattering, which would otherwise disrupt superconductivity. Interestingly, the size of this gap correlates almost linearly with the critical temperature. The larger the gap, the higher the temperature at which the material remains superconducting. Horio's team discovered that the inner CuO2 layer of Hg-Re1223 has a superconducting gap very similar to that of Bi-2223's inner layer, about 62 to 63 millielectron volts MeV. Previous studies had already shown that in Bi-2223, the inner layer's gap is significantly larger than those of the two outer layers, suggesting that the inner layer plays a dominant role in achieving its 110 K superconducting temperature. But here's the twist that could spark debate. The outer CuO2 layers in Hg Ray 1223 exhibit a much larger superconducting gap, 57 millivolts compared to just 43 millivolts in Bi-2223's outer layers. This enhancement in the outer layers appears to be the key factor pushing the critical temperature up to 130 K in Hg Ray 1223, and likely in the original Hg Ray 1223 as well. The researchers emphasize this point in their paper, stating, while strong pairing in the inner plane has been highlighted as the key element of tri-layer cuprates, the present results suggest that the enhanced pairing energy in the outer plane is essential for the highest TC at ambient pressure realized in the Hg dual-based tri-layer cuprate. This challenges the conventional wisdom that the inner layer alone governs the superconducting properties, and invites us to reconsider the role of the outer layers. With the success of ARPES studies on these challenging crystals, the path is now open for even more detailed investigations. Future research will delve deeper into the subtle features of the emitted electrons, enabling precise measurements of the various interactions within and between the QO2 layers. This includes electron-phonon coupling, the interaction between electrons and lattice vibrations, which is believed to influence superconductivity. Such comprehensive studies are crucial for pinpointing the fundamental ingredients that enable high-temperature superconductivity in Hg-based tri-layer cuprates. Ultimately, this knowledge could guide scientists toward overcoming the current limits of critical temperature at ambient pressure, potentially leading to new materials that superconduct at even higher temperatures. This article was carefully crafted by David Apple, edited by Sadie Harley, and thoroughly fact-checked by Robert Egan. We depend on readers like you to support independent science journalism. If you find this reporting valuable, please consider making a donation, especially a monthly one, to help us continue delivering ad-free, high-quality content. For those interested in the original research, see M. Horio et al. Enhanced superconducting gap in the outer CuO2 plane of the tri-layer cuprate. HGRE Bayer2 Ca2 Cu308 plus delta in Physical Review Letters, 2025. DOI 1103 P4C3 T34B, and available on archive at DOI 1048550.08763. Now, here's a question for you. Do you think the focus on the inner CuO2 layer has overshadowed the importance of the outer layers for too long? Could this new perspective reshape how we approach the design of future superconductors? Share your thoughts and join the conversation below.